All right, so what we're going to do now, we're going to do a couple of examples. And again, we haven't learned the equations yet. So all we're going to do is set up the problems. And this is the key. I mean, next chapter is all of the equations. So you're going to be doing all these word problems. And you will not be able to make progress unless you understand this problem-solving method. All right, so make sure you can set up these problems using this problem-solving. Okay, so here we go. Draw a complete pictorial representation for the following problems. Don't solve them because we don't know the equations. Okay, Billy drops a watermelon from the top of a 3-story building. Delinquent. 10 meters above the sidewalk. How fast is the watermelon going when it hits the ground? Wow, what do you say? Okay, now, let's see. First of all, we're going to model it. Now, we're going to ignore air resistance. Is that all right? Well, come on, it's a watermelon. You know, it's not a piece of paper, and it's only 10 meters high. So yeah, that's a good approximation. So we're going to ignore air resistance. And let's see, what else? How many points do we need? Well, you know, it's accelerating at a constant rate. It's gravity. And so all we really need is the beginning point and the end point, right? Now, here's something that's important. And this is an English thing. How fast is a watermelon going when it hits the ground? Well, 0, silly. Well, that's not what they mean, okay? What they mean is like a right before it hits the ground, all right? In other words, if there were no sidewalk there, how fast would it be going, you know, when it reaches the elevation of the sidewalk, okay? So you got to watch the wording, right? So how fast is the watermelon going like right before it hits the ground? That's what they mean, okay? That's what they mean. All right, so let's draw the motion diagram. So it starts here and it ends there, and it's going faster and faster and faster, right? So you can see fast. So, you know, here it's going slowly, faster, 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 right? That's it. And so it's accelerating this way, and the velocity is that way, right? Because it's going faster. Okay, we only need okay, here's our coordinate system. This is going to be super crucial later on. So start getting in the habit now. So, you know, this is up is going to be plus, down is going to be minus. We're going to come to a point where we change our mind on that, and it makes it easier. Okay, so get in the habit. Coordinate system, up, positive, down, negative. We only need 2 points. All right, first of all, it's called the ground zero. We don't have to, but why not? You know, this is the origin. So y initial, v initial, t initial. So y0, v0 is t0, y1, v1, t1. So all you need, right? Because we just already okay, well, we already drew this here. Sometimes I draw it here. It doesn't matter. Okay, so what do we know? We know that okay, this is the origin. So y0 is 10 meters, right? 10 meters. Okay, we got that. 10 meters. Okay, we're dropping it from rest. So v0 is 0. Okay, we're going to assume t0 is 0 because why not, right? Okay, we'll learn this later on, that the acceleration due to gravity is minus 9.8 meters per second squared, minus because minus is down. Okay, now we go over here. So y1 is 0, no kidding. v1, that's what we want to know. So if it were me, I'd put a question mark and I'd circle this thing, right? So I know exactly what I want. And then t1, we don't know t1. So if it were me, I would write t1 equals question mark. And I think that's good later on when you start getting complicated problems. So that's it, all right? I mean, honestly, that's it. But I tell you, if you can do this, you get the problem right. Okay, all right, now, if we were in class, we would have you get into groups, and you would do this. But we can't do it now, so, all right, sorry. A motorist is traveling 20 meters per second. So she's 60 meters from the stoplight when she sees it turn yellow. Her reaction time before stepping on the brake is a half a second. That's pretty bad. She's probably drunk. I don't know. Anyway, so, you know, so what does that mean? It means that from the time she sees the stoplight turn yellow until the time she hits the brake is a half a second, which is really slow. What steady acceleration while braking will bring her to a stop right at the light? Okay, so this is your turn now. So please do it. Don't just look at the answer because that doesn't help you. So pause your video and draw the motion diagram in a complete pictorial representation. This is going to take a few minutes, so not a problem, but do it yourself, please. All right, I assume you did it, so let's do it. All right, okay. So this is the reaction time, right? So this is where she sees the yellow light, and then it takes her half a second before she brakes. When she brakes, she's still moving to the right, and of course she's slowing down, right? See the motion diagram slowing down. But look, if the velocity is this way and she's slowing down, the acceleration has to be that way, right? So the acceleration here is negative. Little things like that really mess people up. You know, if they get the wrong sign of the acceleration or something like that. And so that's why drawing this motion diagram is crucial, because as soon as you see that, you say, ha-ha, A is 0 here, A1 is negative here, you know? A little negative sign, get it wrong, get the whole problem wrong. Okay, now we're going to use the regular, you know, one-dimensional. To the right is positive, to the left is negative. Okay, so we'll say this is the origin, okay? So this is where she sees the light turn yellow. So we have x0, v0, t0, and a is 0 here, right? Then here she starts braking, right? Because we can't just have a beginning and end because something changes, right? She starts to brake, you know? Okay, so x1, v1, t1, x2, v2, t2, right? And here the acceleration is 0 because she hasn't done anything. And here the acceleration is negative. All right, so, okay, so we call this the origin, why not? So x is 0, x0 is 0. How fast is she going? 20 meters per second. We'll call time 0, 0. And we know that the acceleration is 0 here. All right, so we've done this. Now we go over here. Okay, x1 is 10. How do you know 10? Where does it say 10? Well, it doesn't, but you've got to figure it out. So she's going at 20 meters per second, right? And it takes her half a second to hit the brake. So remember, distance equals speed times time. Right? So we want to know the distance. So 20 meters per second times a half a second. Second kills seconds. Half of 20 is 10. Got the units, 10 meters. Right? So x1 is 10 meters. Okay, she's still going 20, right? That's where she hits the brake. So she's still going 20 meters per second, and the time is a half a second. All right, now here, it said initially she's 60 meters from the stoplight. So from here to here is 60 meters. So x2, 60 meters. Okay, what's v2 here? Well, 0, right? She stops. And t2, I don't know, right? All right, now the question is, though, what steady acceleration will bring her to stop? So this is what we want. So I would circle that so I know exactly what I want. Okay, make sure you can do this. All right, let's do another one. So this is American football. You're standing still as Fred runs past you with a football at a speed of 6, oh my gosh, yards per second. Okay, yards per second. He has only 30 yards left to go before reaching the goal to score the winning touchdown. If you begin running at the exact instant he passes you, what acceleration must you maintain to catch him 5 yards in front of the goal line? Okay? All right, so I'll read it again. So I'm going to read it again. All right, okay? So this guy is running past you. He's going to score. You don't want him to score, so you're going to start accelerating and catch him. Knock him to the ground. All right? Okay, so look at, so Fred, all we know about Fred is he's going at 6 yards per second, so no acceleration. But obviously you're just standing there, and then you're going to catch him, so you're going to have a big acceleration, right? Okay, so let's look at the motion diagram. So here's Fred. He just keeps running 6 yards per second. But you start at rest, right? So you're going to go faster, faster, faster. So the acceleration of Fred is 0. the acceleration of u is that way, positive, you know? Okay, we're just going to use normal, plus right, minus to the left. Okay, we have two objects, right? U and, why do they draw a soccer ball? That's weird, whatever. Okay, so you and Fred, all right? And look at, you're starting at the same point, right? And you want to tackle Fred at 5 yards before the goal line. Okay, so here you go. Remember, x, v, a, t. Okay, so for Fred, x, Fred 0, velocity Fred 0. We already know acceleration of Fred is 0, so t 0. Okay, u, x, u 0, velocity u 0, a, u, and t 0. All right? And then we don't have the middle point, we just have the ending point. X, Fred 1, velocity Fred 1, t 1, x, u 1, v, u 1, t. You don't need to write t 1 twice, waste of time. Okay, that's it. So let's just do it. So we're going to say this is the origin, might as well, right? So that's 0 and that's 0. So x Fred 0 equals x, y, u 0 equals 0 times 0 equals 0. Makes sense. Your velocity is 0 because you're starting from scratch. He's already running. So Fred's already going at 6 yards per second. He's not accelerating. You are, right? Okay. Let's go to point 1, where you catch them. So x Fred 1 equals x u 1, 25 yards, right? Because it says there's 30 yards left, but you want to catch them 5 yards before. So it's 25. You got to watch that little stuff, right? You don't want to put in 30, you get the problem wrong. Okay, Fred is still going 6 yards per second. But what do you want to find? Well, according to the question, all you want to find is your acceleration, right? But you don't know your velocity either. But you really want to find your acceleration. So that's how you do it. You have to know how to do this. Okay? Do I repeat myself or what? Okay, so there you go. So next chapter we'll solve these problems. And worse, all right? So make sure you can do the easy stuff now, because it's just going to get really hard. All right, let's review. All we did is concepts, right? We didn't even do any math. Goodness. It's the last time for that. Okay, understand the basic ideas of the particle model, right? We just assume everything's a particle. Simple, right? Just a position, you know? It's not an extended object, just a simple particle. Has a mass, no size. We talked about motion diagrams. They're a tool to help you figure out what's going on. We learned about position, velocity, and acceleration. We recognize the relationship between velocity and acceleration when an object is speeding up, slowing down, turning point. We learned how to add and subtract vectors, problem-solving statements, position versus time graphs, and unit conversions. So let's quickly review. All right, so we learned the head-to-tail method of adding a vector. So there's one vector, there's the other vector, head to tail. That's the sum, that's the total. And again, we don't really care about adding, we really want to learn how to subtract. So a minus b equals a plus a negative b, right? So the only reason we learn how to add is so we can subtract, you know? And that's true. Okay, there's three things: displacement, velocity, and acceleration, or x, v, a, of course, time. You got to know those. If the speed is increasing, a and v have the same sign, both positive, both negative. If the speed is decreasing, they have opposite sign. One's positive, one's negative. The direction of a is the direction of delta v, which is the direction of v final minus v initial. So if you ever want to find the direction of a, which you're going to be doing a lot, trust me, you just have to do this vector subtraction. And it's only direction, right? We don't know anything about magnitude because we don't know delta t. This was kind of cool. This is the turning point. The velocity is 0. Some people think acceleration is 0. That's wrong. Because remember, how do you find the acceleration? It's v final minus v initial, right? And here, it turned out it was this way. So no philosophizing. And do the analysis. And position versus time. So the slope of this is the velocity. Slope of that's velocity. Slope of that's velocity. So this is constant motion, right? The velocity is constant. Then it goes, that's constant, but this is larger than that, and that's larger than that. It's a slope, right? Slope is delta x over delta t. And that's it. Thank you very much.